on your ASRT is things like, specifically they mentioned NCRP report number 160, ionizing radiation exposure to the population of the United States. NCRP stands for National Council of Radiation Protection. I find it interesting that ASRT is using this as a reference since most schools don't really have access to this. This is about a 200 some odd page booklet that costs about, I don't know, $200 or so. So it's a really long report. Probably your test is only going to cover just a few bullet points in it. So let's see if we can cover that.
How do we
So,
get that stuff?
I'm sorry?
How do we get what's on the slides?
You should have a lecture.
Oh, okay, I got it.
There you go.
I
Just
had to,
kidding.
Go further.
Yeah. Okay. So one of the things they're going to ask you about is background. There's a lot of different sources for all of us. So we've got medical, basically, bless you. Computed tomography contributes about 24% of the population. Radiation dose nuclear medicine is about 12%. For the nuclear medicine, basically that's from, bless you.
You don't have to keep saying.
Don't, yeah,
Nuclear
it's done.
cardiology. You're
Yeah.
going to go all night?
Yeah,
All right.
yes.
Exponentially large, bless you.
Thank you. Send me homework.
All right. Interventional fluoroscopy is about 7%, and conventional radiography fluoroscopy medical is about 5%. Consumer is about 2%. Things like your smoke detectors and things like that have very small amounts of radioactive material in them. You've got this little line is occupational and industrial, less than 0.1%. You've got terrestrial background, 3%, internal background, 5%, space is 5%, radon and thoron background is about 37%. This is not something we worry about a lot in the West Coast. Radon is a big deal back in the East and some parts of the Midwest. In fact, in some places, in order to sell a house, you have to have them come in and measure the air quality in your basement. And if they find that the radon is too high, then you have to do all sorts of mitigation things to vent it and bring it down to where it's supposed to be. Total effective dose per individual in the U.S. is about 6.2 millisieverts for 2006. That's double what it used to be. And the doubling is basically due to the large increase, mostly in CT and nuclear medicine. Average annual background, we just saw the big chart, but this is the number of exposed in thousands. This is from 1987, and this is when the previous report would have only been about 3 millisieverts. So between 1987 and now, dramatically increased. Now background is different depending on where you are in the world. You've got areas in Brazil that are up to 10 millisieverts a year. And you've got other parts that are up to 120 millisieverts a year. Kerala, India is about 13 millisieverts a year. Kerala's been studied extensively in the research for radiation safety and protection. I actually worked with a lady at Kaiser who was born and raised there, and Kerala is kind of a population island. It's kind of a very special group, and in studying the population around Kerala versus the people in Kerala, what they found was outside of Kerala the background is much lower, but people in Kerala had some interesting things. Number one, they lived longer. Cancer incidence was less. People were generally healthier, but the background is so much higher than what the surrounding areas were. Now, who can explain it? Hormesis? Who knows? But it is an interesting thing. Then you've got other parts of the world that have varying amounts of background. Other source of exposure, I think I used this slide in another lecture. Air travel, the higher you go and the longer you fly, the more radiation you get. In fact, the FAA has regulations in place to restrict the number of hours that pilots and other folks working on planes can actually fly, how long they can be in the air, how many times they can fly in a month. Sleeping with another person, of course, tobacco, we talked about that. As far as regulations go, this is a quote. This is from the NRC, Nuclear Regulatory Commission. A lot of people get confused because they go, why do we care about NRC? NRC is about radioactive material. In California and in many other states, they take the radioactive material rules and use those over X-ray as well. So for example, here in California, up until, I don't know, mid-80s, basically your radiation safety program was only for people that used or possessed radioactive material. But California and some other folks said no, X-ray is just as much of a concern, so we're going to redefine licensee as anyone that possesses a source, so that includes X-ray. So all of a sudden, this is what requires hospitals to have radiation safety committees that include X-ray and CT and fluoro, as well as nuclear medicine and any kind of therapy that they do, okay? But basically, federal regs don't necessarily supersede state. It gets kind of gray. But this is where the requirements come from. You have a governing body. In this case, this is for whether it's federal, state, or local. You've got a governing body that writes a law that empowers a regulatory agency to write a regulation that implements the law, and they're also responsible for enforcement. Usually regulatory agencies get some advice from advisory organizations, public committees. For the state of California, for anything having to do with radiologic technologists, there's a Radiologic Technology Certification Committee. I served 2 terms on that committee way long ago. And people get confused. The law is usually, think about it this way, the law would be a paragraph, the regulation would be a short story. So the legislature doesn't really get into details of, do this, at what frequency, and what kind of tests or anything. They just say, you will test, you will do. Then the regulatory agency says, how are we going to enforce this? What can we reasonably expect users to do? Okay? There's a lot of disagreement between the regulatee and the regulatory agency. I fought a lot of those battles. It's a pain. So this is an example. Congress writes, for example, the Energy Reorganization Act of 1974, which empowers the NRC to write 10 CFR 20 to implement that law. And then you've got you've got advisory agencies like NCRP, the Health Physics Society, American Association of Physicists in Medicine, AMA, all sorts of those folks basically advising NRC when they wrote that. And then enforcement inspection is down to the user. California works pretty much the same. What we use here is Title 17, which is part of the California Health and Safety Code, although you'll see there's a whole bunch of other things that basically define what you can and can't do in your field. Through the Department of Public Health now, they moved. And these are the folks that are going to come through and ask you things like, who are you? Are you a student? Are you an employee? What kind of exam are you doing? Tell me about how you shield your patients. What exams do you shield for? As a student, you want to avoid these folks. So if you hear that they're in the house, find out from your clinical supervisor either where you can hide or how they want you to handle it if an inspector talks to you. An inspector has a right to talk to any person that they choose. So whether you're a student or not, you could be walking down the hall, they could say, "Excuse me, can I talk to you for a second?" You cannot say no. They have the right to talk to you in private. And they'll ask you, do you have any concerns? Do you feel that you're radiologically safe? Do you have any things that you've seen that you're concerned about? You want to be really careful.
Yo no hablo.
I'm sorry?
No English.
You'd be surprised, they speak several languages. So here's some of the things that I had to deal with that affect what you do, whether you see these regulations or not. You've got Title 21 Code of Federal Regulations Part 1020, which are manufacturer's requirements. This is what tells a manufacturer what they have to do and cannot do with a piece of X-ray or fluoroscopic or CT equipment. 1020-30 is for diagnostic X-ray systems and major components. Point 31 is radiographic, point 32 is fluoroscopic, point 33 is computed tomography. So that's the federal. Then you have the California Health and Safety Code. You've got Title 17, which is the radiation control regulations, which California was the second state in the union to pass those. They were actually passed in 1968, took effect in 69. The only state that beat us to the punch by a couple of months was New York. Then you've got Title 22. Title 22 is for hospitals. This is what tells you when you license a hospital, how many X-ray rooms can you open? Or do you have to have in order to operate a critical care hospital? How many CTs do you have? How many fluoro rooms? How many of anything? What your facilities have to do? Fire control. This basically tells you everything a hospital has to have in order to have a license. Reference Standard Part 12, Title 24, that's the building code. Title 17 and Title 22 are available online. The building code is not. You wonder, what does the building code have to do with X-ray? Building code specifies how you build certain parts of an X-ray room. You have to have communication between the operator and the patient. You have to have shielding. It has to be a window so you can see what's going on. Also specifies the amount of square footage in a room. That's also part of Title 22. Title 10, CFR Part 20, is radiation protection, which now incorporates X-ray as far as the state of California is concerned. And then Title 21, as I said, was Part 1020 is for equipment. Part 900 is the mammography rules and laws. Okay? The agencies involved, tons of them. NRC, the FDA, EPA, Department of Transportation, Department of Health Services, Department of Public Health, county departments of health services. In California, Los Angeles County and San Diego County have contracts with Sacramento to act as their enforcement arm. So when an inspector comes through your facility, most likely for X-ray, it's going to be somebody from the County of Los Angeles, if you're in the County of Los Angeles. If you find yourself working in San Diego, it will be the San Diego Department of Health. Okay? Other than that, it's state of California. Other agencies, we have a lot of folks that contribute input so that regulators don't make decisions blindly. Doesn't mean they make good regulations, but at least they have input from the facility. American College of Radiology sets standards for our community. It accredits radiology practices, advises regulatory agencies. ACR is also the group that certifies by the American Board radiologists, physicists. Joint Commission, big thorn in everybody's side. Joint Commission is somebody that I call a de facto regulatory agency. Medicare will not pay or reimburse any service provided by a hospital that is not accredited by Joint Commission, or I think there's two others that they can accredit with now. Okay. So it's de facto. You don't have that accreditation, you have a problem. National Council Radiation Protection and Measurements, formulates, disseminates guidance and recommendations on radiation protection. There's a whole bunch of other folks that basically provide information. NCRP report number 116 limits, how to limit exposure to ionizing radiation. Again, it's a large document. And that's where they talk about units. So this is where there's some confusion. The original traditional unit of exposure was the Rentgen. It is now Coulomb of air, kilogram per kilogram of air. Okay, there's a conversion. Of everything you see here, the only thing that is measured is exposure. Regardless of what anybody else says, this is the only measured value. Everything below that is a calculated value based on models or some sort of mathematical assumption. Absorbed dose, this is the one you're going to need to know, is gray. Dose is how much energy goes into a particular volume of tissue. Dose equivalent, the Seabird, is how much biologic damage does that amount of energy do. Equivalent dose is if I x-ray different parts of your body, what's the equivalent dose to a whole body dose? Air Kerma is in gray. This is what's displayed on your fluoro equipment, usually milligray per square centimeter. And then effective dose is in Siebert's is also biologic effect. Now the problem is when they calculate patient dose, that's not real. Now there's all sorts of published things you can see on a chart that says, oh, for this particular amount of dose on this particular exam, the dose is X. What they do is that's a population dose. So what they do is they take a demographic group and say for that demographic group, getting this exam, typically they're going to get this amount. But any time that there's a patient dose for almost all exams, that's an estimate. It has nothing to do with the individual patient. It's really important to remember. Patients are going to ask you, well, what was my dose?
Low.
There is no answer to that. Okay. People are working on models to try to develop that. The closest would be Kerma for fluoro and CTDI for CT. You've got all of these definitions. I don't think I need to read them. You can study those on your own. So our sources. In a hospital or medical office, you've got radiography, fluoroscopy. You do have radioactive materials. Unless you're working in nuclear medicine, you don't have to worry about that. Microwave, that is a radiation. I use that in diathermy. But again, unless it's being applied to you, you don't have to worry about that. You won't use that. Lasers. Lasers are an issue for some of the rooms that use laser for positioning. They look small. You don't want to look into them, and you don't want to let lasers go into your patient's eyes. Okay. For those of you working in surgery, there may be times that you're doing mobiles in surgery and they're doing a laser procedure up there. If they're using a surgical laser, you need to have a pair of glasses if you're in the room. So if they're not giving those to you, you need to ask for them. And then, of course, visible light. All right, I think everybody can identify the three sources that we deal with mostly. Primary beam, scatter. So this affects patient, this affects you. Tube leakage, minor. I don't personally worry about that. The only time the tube leakage is potentially a concern is for interventional radiologists who are working and their feet are right next to the tube. There is some leakage that goes through that tube, but again, it's nothing that I ever worried about. Mostly, their feet are going to get backscatter from the patient. So those are 3 sources. Patient protection. Well, you've got to consider what can you modify for intensification and recording? What filtration do you use? How do you control scatter? Repeat, we don't want to do repeats. And any pre or post processing. Yeah, I know, that's a film processor, we don't use those anymore. But we do pre and post processing in the digital world. Filtration is important. A lot of the newer interventional equipment has automatic filtration, so it will change varying amounts of either aluminum and or copper to modify and harden the beam for different types of procedures. Field size. Collimating to the area of interest is crucial. A lot of radiologists don't seem to understand that, but fortunately our technologists do, because this is how you keep dose and scatter at a minimum. Patient shielding. In what situation is shielding required under California law?
All situations.
All?
If it doesn't interfere
Here
with
with
the
study.
Regulations don't say all.
Childbearing age.
There's only 2 situations in regulation where shielding is specifically
Is
required.
that when you're within 5 centimeters of the gonads?
Gonadal shielding, as long as it doesn't what?
Interfere with the primary beam.
Interfere with the diagnostic information in the exam, and what else? Anyone working or in a fluoroscopic room where it's 5 MR per hour or greater must have at least a 0.25 millimeter lead aprons. That's your protection. Other than that, shielding is recommended. Shielding has an interesting history, just to let you know. The original x-rays, if you remember the history lecture I did, remember those were circular fields of view. So if you have a circular field of view and you're doing a 14:17 image, what happens? If you're doing a chest x-ray and it's a round field of view, what are you doing? You're irradiating the neck, you're irradiating gonads from the back. So that was the idea behind shielding. Before rectangular collimation existed, you had to shield the patient for things like chest x-rays because that circular cone went into that area. Since then, it's really a comfort thing. Patients feel better when they're being shielded. Every hospital has their own particular protocols for when you shield and when you don't. You need to know what those are in the hospital that you work at, because that's what you're going to be held to. Anyway, time, you want to keep your time short, and of course, distance, your SID and SSDs are important. This was the old days. Don't have to undress, just turn up the power, right? We don't do that. Typical patient doses, thermography, chest x-ray, ERCP, abdominal CT, bone scans in nuclear medicine, cardiac. Okay. People look at these when you convert them to milligray or gray. This would be 0.4 gray, 0.8 gray. People get all excited. Diagnostic doses in very few situations create an appreciable risk of effect. Okay. There are some areas that you do have to be cautious. Interventional. Interventional, when I worked as a tech, we did angios. So we did aortograms, we did carotids. That was pretty much it. That was the world. Nowadays, They're doing everything under the sun. They're doing interventional. They're replacing things inside that used to require surgery, and now they're doing it all interventionally. My brother had a heart valve replaced interventionally through 2 little slits in his chest, went home the next day. Those exams, though, can provide a lot of fluoro time. It's quite common for some complicated interventional procedures for 60 minutes of fluoro, not procedure time, but fluoro time. I've seen some procedure times where there's up to 120 minutes of actual fluoro time. And we talked about what you have to be concerned about: reddening of the skin, possible loss of hair. Also, you have to worry about who's in the room. You've got to worry about your techs, your nurses, physicians. Pediatric doses, these are typical. We do try to keep things down. Anybody here, you guys have all heard of image gently, image wisely. Who has not heard of them? Image gently is a protocol. Happen to have them. Da-da-da. This is really important. They have a website. You can actually go online. And they talk about patient disclosure. And this is in your reading for next week, which is the current issues in radiation dose monitoring and reporting from the ASRT. Image gently is for children. Image wisely is for adults. And basically, the things that you need to consider as technologists: you have to consider the patient's safety and risk of radiation effects. You have to optimize the use of radiation. You're required to share strategies for selecting the most appropriate imaging examinations with referring physicians, and continuously review examination protocols to ensure that current exposure techniques and dose-limiting tools are used effectively. Now, those are recommendations. However, I guarantee you, when Joint Commission comes through, they're going to ask, do you follow image wisely? Do you follow image gently? It's great because they have websites for that. You can actually go on site yourself, take the little test, and get a little printed certificate